All right, Algebra 2. We're talking Lesson 10 today. The power of algebra. Finding Pythagorean triples. The point of today is showing how this polynomial identity can be used to generate Pythagorean triples. So, a Pythagorean triple, you remember the Pythagorean theorem, which is A, BC, A squared plus B squared equals C squared. The Pythagorean triple that I've just always had memorized is the 3, 4, 5 triangle, which satisfies this equation, A squared, B squared, C squared. So if A is 3, we have 9 plus 16 equals 25 every time, okay? The Pythagorean theorem is just arguably one of the most important theorems in geometry. We use it a lot in many different ways. So that's what we're going to get into today. Okay, let's try our opening exercise. Sam walks 1 block north, 1 block east, 3 blocks north, and 3 blocks west. So let's do that. We have our starting point. So 1 block north, 1 block east, 3 blocks north, and 3 blocks west. Cool. All right, Jill started at the same spot. She walked 4 blocks south. So we start here. 1, 2, 3, 4. 4 blocks south, 1 block west. That's about a block. 1 block north. And 4 blocks east. 1, 2, 3, 4. All right. If all city blocks are of the same length, who is the farthest distance from the starting point? Starting point, who is the farthest distance? So we're trying to figure out that distance and that distance. So really, I need to connect, excuse me, that. Okay, so we really have a triangle and a triangle, right? The distance here is 1, 2, 3, 4. Distance here is 2. We don't know what that is. That should be a C though, not a C prime. Here we have 1, 2, 3, 1, 2, 3. So let's write that down. 3, 3, and C prime. So let's figure out what our diagonals are. First, we're going to talk about Sam. So we have 2 squared plus 4 squared equals C squared. 4 plus 16 equals 20. Square root of both sides, C equals the square root of 20. Talk about Jill. I have 3 squared plus 3 squared equals C prime squared. That is not C to the 12th. 9 plus 9 equals 18. C prime squared. Square root of both sides. C prime equals the square root of 18. Cool. So Sam's distance is the square root of 20 city block lengths, and Jill's distance is the square root of 18 city block lengths. So Sam is actually farthest away from the starting point. All right. So who walked the farthest? We had our starting point. Sam really walked a long distance before we get back to the beginning. Not sure if that's quite the path he took. Yep, we went 1 block over, up, over. So we had to get from here back to the beginning. So he technically walked or really far away if we counted up sort of his path. But when you're trying to figure out distance from the beginning, you have to make a right triangle to figure out how far I went here, how far here, to figure out what our distance is using Pythagorean theorem. So this is really irrelevant to our equation. So if the question was, who walked the furthest, our answer would be different because Sam's trip was much different than Jill's. You know, we went over and back. They're very different trips. So we didn't ask who walked the furthest. We asked who was the furthest from the starting point, which is the distance here. You may have heard sometime in the past, as the crow flies. There may not have been a direct path from where Sam ended up to the beginning. He'd have to leap tall buildings, cross many streets. This is not a straight path, but it's what the question was asking. How far is Sam from the start point? So this is an as the crow flies, because a crow can fly over buildings. A crow doesn't have to jog around hot dog vendors and other random things. So that's why we'd say as the crow flies. We also didn't really take into account, like, as he's walking this direction, crossing streets, etc. Maybe one street was 4 lanes, another street was only 2. We really didn't take all of that into account. So you have to make some assumptions when you're working on problems. The other thing I want to make sure I point out is the square root of 18 is going to be smaller than the square root of 20. You can calculate it, but if the number underneath is smaller and you take the root of it, it's going to be a smaller number. So you're good with that. So that's why we use the Pythagorean theorem. We can do an as the crow flies problem. And we already did that. Okay, first example. Here we're going to explore a specific case of the general method for generating Pythagorean triples. And Pythagorean triples are positive integers, a, b, and c, that satisfy a squared plus b squared equals c squared. And they have to be integers. Okay, integers are positive whole numbers. And that's what we're working through. Okay, so I'm going to erase that. Nope. So let me erase that so we have room to work on example 1. Okay, let's get a picture here. So prove that if x is greater than 1, then a triangle with side lengths x squared minus 1, 2x, and x squared plus 1 is a right triangle. And if you remember with the Pythagorean theorem, a, b, and c, c is always the biggest number. A is the smallest, and b is in between. So let's figure out which one's the smallest, biggest, and in between. I mean, if I just say, okay, x equals 2, just pull that one out. 2 squared is 4 minus 1 is 5. 2 times 2 is 4, and 2 squared is 4 plus 1. Oh, goodness. Hold on. 2 squared is 4 minus 1 is 3. Thank you very much. Not a mistake if I catch it myself. X squared, 2 squared plus 1 is 5. So we have our small, big, and medium. So let's put them in the right place. Our biggest one goes in the C spot. Our smallest one goes in the A spot. And the in-between one in the B spot. So let's go ahead and put that into the Pythagorean theorem. and work through some math. I wrote on the first slide of the lesson that we're trying to use a polynomial identity. So let's see if we can do it. Okay, a squared plus b squared equals c squared. Okay, if you guys could go ahead and work through that, I'm going to push pause and do it on the side. Okay, first thing I want to point out is I forgot to write that squared right there, so I fixed that. I expanded this polynomial right there, multiplied this right there, and expanded this one right here. Did some algebra. I have positive x4 on one side, positive x4 cancels out. I added 2x squared to both sides, got 4x squared, positive 1 cancels. I carry this down, I'm left with 4x squared equals 4x squared, which is true, it's an identity. So what we are proving is, what I've proven is that this is true, this being our Pythagorean theorem, and the identity that I wrote on the first slide, which is the one we're going to use to prove Pythagorean triples, is x squared plus y squared quantity squared equals x squared minus y squared quantity squared plus 2xy quantity squared. Okay, I don't have any y's in my first example, but I can rearrange this. Actually, it doesn't need rearranged. I just have it written in a backwards order. I have this piece, which I wrote first, and this piece, which I wrote second. Okay, and to remind you that a Pythagorean triple, hold on. Pythagorean triple is going to be any integers, a, b, and c, which are positive integers that satisfy the equation a plus b equals c. And to remind you the example we just used, I had x squared minus 1, 2x, and x squared plus 1, which gave me 3 integers that satisfy the Pythagorean theorem. So I've said that, 3, 4, and 5 is a Pythagorean triple because 3 squared plus 4 squared does in fact equal 5 squared. What about 1, 1, and the square root of 2? Is that a Pythagorean triple? Okay, 1 squared plus, 1 squared, does that equal the square root of 2 squared? 1 plus 1 does in fact equal 2. But 2, or square root of 2, is not an integer. So it can't be a Pythagorean triple. So I also want to note that any multiple of a Pythagorean triple is also going to be a Pythagorean triple. So we've talked about 3, 4, 5 is a Pythagorean triple. That means that 6, 8, and 10 is also going to be a Pythagorean triple, or 9, 12, and 15, etc. Any multiples of any given Pythagorean triple is also going to be a Pythagorean triple. So I can just say that any number times A, same number times B, same number times C will be a Pythagorean triple. Okay, the exercise 1 that we did gave us 2x, x squared minus 1, x squared plus 1. I can pick x equals any number. Let's just pick, I don't know, 10, and come up with Pythagorean triples every time. So x squared minus 1 would be 100 minus 1 is 99. X squared plus 1, 100 plus 1 is 101, and 2x is 20. So a squared plus b squared should in fact equal c squared. Okay, hold on a second. So I don't know those squares at all. 99 squared is 9,801, 20 squared is 400, and 101 squared is 10,201. So if we add these together, we do in fact get 10,201 does equal 10,201. So our first example will help us find any Pythagorean triple. Cool. Okay, let's look at example 2. So it's just going to be a clever way for you guys to remember that x squared minus 1, 2x, and x squared plus 1 can be used to find a Pythagorean triple. So the instructions here say, next we describe an easy way to find Pythagorean triples using the expressions from example 1. Look at the multiplication table below. Notice that the square numbers, 149, etc., 81, lie on the diagonals of this table. Right through the middle. Okay? What value of x is used to generate the Pythagorean triple 15, 8, and 17 by the formula x squared minus 1, 2x, and x squared plus 1? How do the numbers 1, 4, 4, and 16 at the corners of the shaded area in the square, at the corners of the shaded square in the table relate to the values 15, 8, and 17? So let's look at it. So using the value for 4, using the value for 4, the value of 4 for x, that gives us the triple 15, 8, and 17. We see that 1 squared, or 1 equals 1 squared, 16 equals 4 squared, and then we can take 16 minus 1 is 15, and 16 plus 1 is 17. We also have 4 plus 4 equals 8. Cool? So I've got my numbers right there. Let's try another one. Form a square on the multiplication table below, whose left top corner is 1, as in the example, and whose bottom right corner is a square number. Doesn't matter what, just find a square number. So I'm going to grab these. Okay? And I'm going to circle the corners, just like the previous example. Cool. So here I have 25 minus 1 is 24. 5 plus 5 is 10. 36 plus 1 is, 25 plus 1. I was looking at something else. 25 plus 1 is 26, and 25 minus 1 is 24. So let's look at the triple of 10, 24, and 26 and see if it works. So 10 squared plus 24 squared, does that equal 26 squared? Hold on a second. So yes, in fact, it does work, because 100 plus 576 is in fact 676. Cool. Right, example 2 still continued. So let's generalize this square to any square in the multiplication table where two opposite vertices of the square are square numbers. Okay, so my opposite vertices right here are square numbers. So how can you use the sums or differences of the numbers at the vertices of the shaded square to get a triple, 16, 30, and 34? Is this in fact a Pythagorean triple? So following what we did above, I'm going to take 25 minus 9 equals 16, and 15 plus 15 equals 30, and 25 plus 9 equals 34 to get the triple 16, 30, and 34. And if I do that math, 16 squared is 16 squared is not 900. 30 squared is 900. 16 squared is 256. And 34 squared is 1156. Add those together, I get 1156. So yes, it is. Okay, using x instead of 5 and y instead of 3 in your calculations in part C, write down a formula for generating the Pythagorean triples in terms of x and y. So the first calculation I had was 25 minus 9, and that gives me x squared minus y squared. The second calculation I had was 15 plus 15 equals 2 times 3 times 5, which gives me 2xy. And I don't need parentheses around that though. Let's get rid of those. 2xy. And the last calculation I had was 25 plus 9, which is x squared plus y squared. Okay, do you see the pattern now? It's sort of cool how it all worked out. So it seems the Pythagorean triple can be generalized and generated by x squared minus y squared, 2xy, and x squared plus y squared. That's so cool. So in the problem sets, you're going to use this to find Pythagorean triple, mimicking what we did in example 1. So in closing, Pythagorean triples are triples of positive integers. Integers are whole numbers that satisfy the Pythagorean theorem relationship. Such a triple is called a Pythagorean triple because a right triangle with legs of length A and B will have a hypotenuse of length C using the Pythagorean theorem. So to generate the Pythagorean triple, we can use those forms, those equations, and our relevant vocabulary. Excellent work today. That was a lot of fun.